The electronic description of atoms provides the basis for a discussion of the microscopic properties of atoms as opposed to the macroscopically derived properties like density, valence, color, and so on that Mendeleev used. By microscopic, we mean properties of individual atoms such as their size. Let's look at the relative sizes of atoms as an example. Here are some experimental data on atomic sizes of the atoms of some of the elements. These data were obtained from a variety of experiments which shall not be discussed here. The data are displayed pictorially here by placing the element in its appropriate place in a periodic table-like arrangement. The atoms are depicted as spheres, and the spheres are scaled relative to each other. The numbers below the cartoon spheres are numerical values of the atomic radii in angstroms. Two trends in the experimental data are immediately obvious. The elements decrease in radii as we progress across a period from left to right. For example, consider the element cesium through radon. The second general trend in atomic radii is that within a family, the elements increase in size as we progress down a given family from top to bottom. Now let's look at the microscopic interpretation of the trends in the atomic radii using the wave mechanical nuclear model of the atom that has been developed. In a general way, an atom can be imagined to consist of a nucleus surrounded by an ill-defined electron cloud. The electrons are constrained by the nuclear charge. As the nuclear charge increases, we might expect that the electron cloud would be more tightly held, that is, pulled closer. In this case, a group of atoms should get smaller as the nuclear charge increases. However, as electrons are added to the outer shells, an increase in the principal quantum number, we might expect that the electron cloud would be less tightly held and the atoms would get larger. The trends in the atomic sizes are indicated in this cartoon. The central figure is a representation of the long form of the periodic chart. The atomic sizes increase from right to left and from top to bottom. The trend is apparent in the experimental data that are available for the elements and is generally predicted from our microscopic model of the size effects as predicted from the nucleus electron cloud interaction arguments described earlier. There are, of course, a few inconsistencies in the data which are for the most part unimportant when considering general trends. This is a happy condition when experimental results seem to reflect relatively simple theoretical ideas. The relative sizes of ions, both cations and anions, also follow trends predicted from the microscopic model of the atom. We start with the neutral atoms for which we know the trends. Cations are formed from neutral atoms by the loss of electrons. Thus, cations contain the same number of protons in the nucleus as the neutral atom, but they contain fewer electrons. In other words, the electron clouds of cations are less diffuse, so that the electron cloud would be attracted more strongly in cations. All of this is to say that cations should be smaller than the corresponding neutral atoms, and perhaps more importantly, trends in the sizes of cations along a given period or down a given family should be the same as for the neutral atoms. Look at the data for the cations on the left side of the table. First, the cations increase in size down a family, and they decrease in size across a period. It is not possible to go beyond group 3A because the elements in higher numbered groups do not form cations easily. In addition, the original data that cations are smaller than corresponding neutral atoms appear valid. Only the data for family 3A atoms and the corresponding cations are illustrated here, but be assured that the corresponding data for other pairs of atoms and cations follow the same general trend. Now we turn our attention to anions, which are formed when neutral atoms acquire an electron forming a negatively charged species. In anions, the electron cloud carries more charge than the original neutral atom possessed. Thus, relatively speaking, fewer positive charges are available to attract the electron cloud, which then becomes less strongly attracted. The net effect is that the electron cloud for anions exists further away from the nucleus than in the neutral atom. All this predicts that anions should be larger than the corresponding neutral atom. The relevant data for anions appears at the right side of the diagram. As predicted, the anion species decrease in size going from left to right, and they increase in size going from top to bottom. Furthermore, a comparison of the size of the atom in group 7A shows that an anion is indeed larger than the corresponding atom.